Hi there, this is Soman and you're watching the Genesis YouTube channel. Today we'll discuss a problem that I have dubbed a beginner's guide. Why this name? It is so because the solution to this problem encapsulates the various points that you must keep in mind while solving these kind of problems. There will be other beginner's guide problems that will appear in the channel. Watch them closely as it gives you an insight into a large category of problems that you can solve. So without further ado, we jump to the problem. A uniform solid cylinder of mass m and radius 2r rests on a horizontal tabletop. This is shown in the figure. A string is attached to an axial axle through the center of the cylinder so that the cylinder can rotate about the axle. The string runs over a pulley C in the shape of a disc of mass m and radius r that is mounted on a frictionless axle through its center. A small block B of mass m is suspended from the free end of the string. There is sufficient friction between the string and the pulley to prevent slipping. Also, sufficient friction exists between cylinder and the tabletop to prevent slipping. Neglect friction at all other contacts. After the system is released from rest, what are the accelerations of A, B and C? Also find the tensions in the straight segment of the string, friction acting on the cylinder and force on the pulley C from the hinges. I suggest that you take a pen and notebook and work the problem as the solution progresses. Frequently during the solution, I will ask you to evaluate certain steps. At those points, stop the video and do the required calculations. Also, important steps will be highlighted on the screen with a yellow patch. Keep watching out for that. We will solve this problem with two methods in this video. First, by force-torque method, which I will call the dynamics method, and second by energy considerations. So first, the dynamics method. Let the acceleration of the center of A be a1 rightward and angular acceleration of A about the cylinder axis be alpha1 in the clockwise sense. The angular acceleration of C, let it be alpha3, and the acceleration of block B, let it be a2 downwards as shown in this figure. Now in all such problems, you will have to decide the direction of friction. The friction is static here and you could, if you wished, take a random direction and proceed. If your answer for friction came out positive, that means your assumed direction was correct. If it came out negative, then friction is in the opposite direction. But you can do it only for static friction. However, as an mental exercise, you should try to find the direction of friction acting if you can. So can we do that here? Yes. Imagine what would happen to the cylinder if there was no friction. If there was no friction between the cylinder and the table, the tension would have pulled the cylinder translationally rightward. Why translationally? Because the tension is passing through the center of the cylinder and it would not give any torque. Now this would have caused the point of contact with the table to slip to the right. To prevent this, static friction must act to the left. With the direction of friction decided, I suggest that you pause the video and try to draw the FBDs of the system. I hope you have done that. The free body diagrams of A, B and C are shown. Hx and Hy are the hinge forces on C. Now stop the video and try to write the dynamics equations yourself. I hope you have done so. So here are the equation of dynamics. N is equal to mg, T minus F1 is equal to ma1. The torque of the friction force about the center of the cylinder is F into 2r, that is equal to the moment of inertia into the angular acceleration. Moment of inertia here will be half m into 2r whole square because it's a cylinder, half m radius square. Now for the torque equation of C, T2 is giving a clockwise torque, T1 is given an anti-clockwise torque. So T2R minus T1R is equal to half mr square into alpha 3. Translational equations of C, Hx is equal to T1, Hy is equal to T2 plus mg. And finally, for the block B, mg minus T2 is equal to ma2. Now we come to a very crucial step. Usually, students proceed blindly without taking into account how many variables they have introduced. With practice, you will be able to write the relevant equations. However, for beginners, I advise that you write all the equations clearly. Why, you ask? Observe that we have 10 variables n, f, t1, t2, hx, hy, a1, a2, alpha 1, alpha 3. But only 7 dynamic equations. So where will the rest come from? Can we solve 7 equations for 10 variables? No. We need 3 more equations. So where will they come from? Constraints. The rest 3 will come from constraints. Now usually beginners may write 1 or 2 constraints and then obviously they will get into trouble. Now just by doing a little accounting, you can see that there are exactly 3 constraints required. You should be aware of this at all times. Shooting blindly in the dark and hoping for correct answers usually does not work. So how do we get the constraints? We get them by the conditions of no slipping and inextensibility of the strings. Look at A. The bottommost point shouldn't slip relative to the point below it on the table. Also, the portion of the string between A's center and the top of the pulley C is taut, and so is the portion of the string from pulley C to the block B. Now this figure shows the velocity of various points of interest. Now as the system is starting from rest, the velocities are just accelerations multiplied with time. So you can see for A, it is a1t and alpha1t. Now as there is no slipping between A and the table, at the bottommost point we'll have two velocities a1t directed rightward and omega r alpha1t into 2r, because the radius is 2r, leftward. So a1t should be equal to alpha1t into 2r. Cut out the t, you will get a1 is equal to 2 alpha1r. Now for the segment of the string between the center of the cylinder A and the top of the pulley C, now if this is to be taut, we must have the velocity of one end along the string equal to the velocity of the other end along the string. So you can see that the velocity of the end of the string attached to the center of A is a1t, and on the other side we have the velocity omega r, which is alpha 3t into r. Equating these two, we get a1 is equal to alpha 3r. Similarly, I hope you can write the constraint for the string between the pulley C and the block B, and this will come out to alpha 3r is equal to a2. A general word of advice: always write the constraints in velocity or displacements and then get the relation in acceleration, if any. Here, since the system started from rest, it wouldn't have mattered, but we will see questions where it does make a difference. So just keep this in mind: constraints in displacements or velocities and never in accelerations directly. Now we can combine the constraint equations and we can see that a1 is equal to 2 alpha 1r is equal to alpha 3r is equal to a2. We just combine them into one single equation. Now manipulating the dynamic equations with these constraints, I leave it up to you to show that you will get these set of equations: t minus f1 is ma1, f is equal to half ma1, t2 minus t1 is half ma1, and mg minus t2 is m into 2a1. You realize I have converted everything on the right hand side in one single variable a1. Add all this up, you will get a1 is equal to g by 3. Once you get a1 is equal to g by 3, everything else you can find from these four equations. So you get a1 is equal to g by 3 rightward, alpha 1 g by 6r clockwise, alpha 3 g by 3r clockwise, and a2 g by 3 downwards. And now using the original equations, I can find out the friction is 1 by 6 mg, t1 is mg by 2, t2 is 2 mg by 3, hx mg by 2, hy 5 mg by 3. Now these calculations, I trust once I have given you the values of a1, a2, alpha 1, alpha 3, you will be able to get on your own. If required, pause the video and work this out. Some beginners start worrying about the fact that the cylinder A possibly hits the pulley C. But note in that question, the initial lengths of the straight segments of the strings were not given. Neither is the data sufficient to analyze the nature of collision between A and C. So it is apparent that the question framer doesn't want you to extend the analysis till that instant. Read the question carefully and try to avoid unnecessary and unfruitful distractions. Undisciplined imagination usually leads to chaos. We now get on to the second method, which is the energy method. The accelerations are chosen as before. As the system is released from rest, at time t, the velocity of the center of A will be a1t, angular velocity of A about the cylinder axis will be alpha 1t clockwise, angular velocity of B will be alpha 3t, and the velocity of B will be a2t downwards. Further, the block B falls a distance of half a2t square. The constraints are as before. We have this three set of constraints. Now just look at the three set of constraints. We have four variables: a1, a2, alpha 1, alpha 3. So four variables and only three constraint equations. We need one more equation, and this will come from the energy equation. So here now, instead of working with 10 variables and 10 equations, we have straight away reduced it to 4 variables and 4 equations. Now the forces acting on the system A plus B plus C are shown. The static friction F on A, normal force N on A, the hinge force Hx and Hy acting on C. Why doesn't the friction do any work? Because the point of contact is at momentary rest, so its displacement is 0. Secondly, the normal force acts perpendicular to the direction of displacement of A, so it does no work. Why do the hinge forces do no work? Because the point of application of Hx and Hy does not move. Also, as the string is inextensible, the total work done by the tensions is zero. This, I hope you know from your particle mechanics. Now we take the system as A plus B plus C plus Earth. Now the external forces do no work and there are no internal non-conservative forces in the system. Hence, mechanical energy of the system is conserved. Take zero potential level for gravitational potential energy of A at the level of its center. Take the zero potential level for the pulley C at the level of its center and that for block B at its initial level. So we now conserve mechanical energy. Now you see these equations, you will see a lot of zeros and there is a lot of grouping that I have done. So listen carefully as I explain. Now look at the group of first three zeros. Those are the initial energies of the cylinder A. First zero is for the gravitational potential energy. Second zero is for the translational kinetic energy. Third zero is for the rotational kinetic energy. Corresponding to that, if you see on the right hand side, you can see three terms clubbed together. The center of A has not changed its height and therefore its potential energy remains zero. That is the first zero. Second term is the translational kinetic energy half mv square, half m into a1t whole square. Third term is the rotational kinetic energy, half moment of inertia into omega square, half I omega square. So half into moment of inertia of that cylinder, half m into its own radius square, which is 2r given in the question. So 2r square into omega, which is alpha 1t square. Plus, now look at the second set of zeros on the LHS. That is for the pulley C. The first zero in this pair is for the gravitational potential energy of C and the second zero is for its rotational kinetic energy. Correspondingly, you can see that on the right hand side, we have the potential energy remains zero because its center has not changed any height. And the rotational energy is half I omega square, which is half into half mr square into omega is alpha 3t whole square. Now on the LHS, we have another pair which is clubbed together. The first one is for the potential energy of block B and the second one is for the kinetic energy of block B. Initially both were zero. Now look at the corresponding club terms on the RHS. You can see that the block has fallen by half AT square and therefore the potential energy will be minus mg into half A2t square. And what is the kinetic energy? Half mv square, so half m into A2t square. I strongly suggest that initially you write out the zero terms. The simple reason is that if you see that there are 7 terms on the LHS, there must be 7 terms on the left. It is a usual complaint among students that they forgot an energy term. This way you will never lose an energy term. Later, with practice, you will be able to write the energy equation correctly without writing the zeros. Till you feel confident, I suggest that you neatly write down each term. Now cancelling out the factor half mt square in this equation, substituting alpha 1 is equal to a1 by 2r, alpha 3 is a1 by r, and a2 is equal to a1, we get an equation like this. Now you can see that here also a1 cancels out. And if you solve, you will get a1 is equal to g by 3, alpha 1 is g by 6r, alpha 3 is g by 3r, and a2 is g by 3 as we had seen before. After this, I leave it up to you to show that you get the same answer for the other asked quantities. Now in later videos, I will show you how to approach the same question in an examination where time is limited. There are several reductions possible which will save your time. However, I consider it critical that you learn at least how to write the basic equations and solve using dynamics and energy. So I hope you enjoyed this problem. If you learned something from it, like, share and subscribe. And as always, stay safe and stay healthy.